On page 2, we're going to look a little bit more at propositions, work on propositions. So on number 4, it says that endpoints are placed inside a triangle. Non-intersecting line segments are drawn connecting the 33 vertices of the triangle and the points within it to partition the given triangle into smaller triangles. So make a proposition concerning the maximum number of triangles obtained in the general case. Okay, so in the first example, we have n equals 1. So basically we drew one dot inside the triangle, and then we connected that dot to the vertices, and that formed 1, 2, 3 triangles inside. So that basically made 3 internal triangles from the outside triangle. Then we're going to draw 2 dots in the interior of the triangle, and then if we take those points that we drew in the interior of the triangle and connect them to vertices without intersecting, right, because it says non-intersecting line segments, then we end up with a drawing similar to this one here. And if we count the triangles here, we have 1, 2, 3, 4, 5 interior triangles there in that case for n equals 2, right? And so let's look at n equals 3. For n equals 3, we have 3 points drawn in the interior of the triangle. And if we connect all these points to each other and to the vertices without having any intersections, then we basically have 1, 2, 3, 4, 5, 6, 7 interior triangles. And then if we look at the pattern here, we see 3, 5, 7, and then we may conjecture that if we had n equals 4 and so on, that we would be counting up in odd numbers. Okay, so we could say that for n equals 1, it's 3. For n equals 2, it's 5. For n equals 3, it's 7. And for n equals, or for n, it would be, let's see, 2n plus 1, something like that. So even numbers would be 2n. Odd numbers would be 2n minus 1 or 2n plus 1. In this case, you can check to see with n equals 1 that it would be 2n plus 1. So we might say as our proposition that the number of triangles, if we have n dots inside the triangle, the number of interior triangles, if we have n dots inside the main triangle, would be equal to 2n plus 1. For n is a positive integer, and n is greater than or equal to 1. If n points, this is number 5, if n points are placed around a circle so that when line segments are drawn between every pair of the points, no 3 line segments intersect at the same point inside the circle, we consider the number of regions formed within the circle. Okay, so if we have 1 point around the edge of the circle, we obviously can't really connect it to any other point, so that we just have one region inside the circle. It's not cut at all. If we have 2 points on the edge of the circle, we can connect the 2, and then that forms 2 regions, right? If we have 3 points on the edge of the circle, we can connect those with these 3 line segments. We end up with 4 regions, right? And basically we do not want 3 line segments to intersect at the same point inside the circle. So we'll see exactly how that would happen maybe later. Let's do A, which says draw the case where n equals 4 and n equals 5. So this is n equals 4 here. So first what you're going to draw, we're going to connect them like that, and then we're going to connect them like that. Is there any other way we can connect them? No, there's not. So how many regions is that? So there's 4 triangle regions and 4 little orange piece regions. So that would be a total of 8, right? Now let's do the n equals 5 case. So n equals 5 would have 5 dots on the edge, 5 points on the edge. And then we connect them together. It would make a pentagon. We would connect them to each other, and it would start making a star. Is there any other way we could connect them? No, I think that's it. So let's see. We got 1, 2, 3, 4, 5. We got 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we got 16. Okay? So if we start looking at the pattern here, we got 1, 2, 1, 2, 3, 4. 1, 2, 4, 8, 16. Do you see the pattern there? So each number is multiplying the previous number by 2. So it looks like we could say that the conjecture for larger cases might be something like 2 to the n. Okay, always be multiplying by 2. Let's see, but if we put n equals 1 in there, it would give us 2, and we want n equals 1 to give us 1. So let's make an adjustment. It would be 2 to the n minus 1. Okay, then that would give us this pattern here. So like, for example, if we had n equals 5, we would get 2 to the 5 minus 1. 5 minus 1 is 4. 2 to the 4th is 16. So that works, right? Now it says to draw the case for n equals 6 and see if we still believe our conjecture is what they say. So first of all, let's shrink this down a little bit. Okay, and then let's draw a big circle, and then we're going to see if n equals 6 works. Oops, that's awful. Okay, and then so remember, 6 is like a hexagon, so we could kind of draw it like that, and start connecting all the points. Don't forget about these. Okay, so let's see, 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, 4, and 1, 2, 3. Okay, am I done? That kind of looks done. Okay, so now I'll start counting the region. So this is 1, 2, 3, 4, 5, 6 on the outside. 1, 2, 3, 4, 5, 6. That's 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And right here in the middle, there's 31. So 31. Is that what we expected? Well, actually, our conjecture was that it would be 2 to the n minus 1. If this is 6 points on the outside, 2 to the 6 minus 1 is 2 to the 5th. We were expecting to see 32. We saw 31 in this case. So what does that make us think about the conjecture? We don't believe it anymore. That's kind of weird, isn't it? All of a sudden it just looked like it was going good, and all of a sudden it didn't work.